are just beginning chapter 3 of this book right here, Causal Inference in Statistics. So let's go down to the question. So the first question in 3 has, let's see, 4 parts, A through D. Oops, A through D here. So we'll read them as we come to them. But what's important is that this is piggybacking off of question 1.52 and figure 1.10 in that question. And so I've reproduced that question and the figure here. The basic idea in that question and also here is that we have this system where people are receiving treatment X based on the presence or absence of a syndrome Z, and their outcome is going to be determined by both X and Z. Okay, and in the question, if you go through, I'm not going to detail it in gory detail here. I'll let you kind of read through it. But you know, like the probability of receiving a treatment or not receiving a treatment, given the presence or absence of the syndrome, etc., 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 are given different probabilities that are just generically encoded as something like P, you know, P1, P2, Q1, Q2, Q2, etc. Okay, so I'll let you get familiar with those things. I will speak on more of a general level here because it will be a little bit too confusing if I just continually refer to P1, Q1, so on and so forth. Okay, so so part A here, we are meant to compute probability of Y do X for all values of X and Y by simulating an intervention do X on the model. Okay, so now, remember that the do operator is a way of simulating a randomized intervention on a system. Okay, so in other words, it is, so in our data right here, it is probably the case, given the context of the question, that the people that were receiving the treatment was not random. It was based on Z here. Okay, and because Z is also affecting Y, then there is this confounding factor for the outcome of Y, which is Z, right? And so what we want to do is we want to simulate randomizing treatment, okay, regardless of syndrome. Okay, so so the way that we do this visually is if we were just to delete or cross out this arrow right here from Z to X. Okay, but that, I mean, you know, I can say that and maybe that gives you some intuition about what's going to happen. But mathematically, you know, what does that mean, you know, mathematically? And so the way that we do this mathematically is with this expression right here, where we marginalize over the confounding variable, in this case it's Z. Okay, so so we take the conditional probability of Y given X and Z for all possible values of Z, and by doing this, we are what is called marginalizing out Z. In other words, we are looking at the probability of Y across all different values of Z. Okay, so that's the expression right there, and we can get there. Let's actually derive it, and the way that we might derive it is with the following expression. So we begin with the joint probability distribution of all of our variables, and then we are going to condition on what's called the propensity score, which describes the propensity to receive treatment, okay, given whatever other variables are determining that treatment. Okay, so so now if we so the reason that we condition on the propensity score is this is just our definition of conditional probability, right? Probability of A given B is the joint probability of A and B given B. And so here B is representing our propensity score. It's the probability of receiving treatment given condition of the syndrome. okay, whether or not you have the syndrome, Z. Okay. So this again is just the, let's continue. So we can factorize this joint probability, right? We can do y given x and z, right? Because y is informed by both x and z, times the probability of x given z, times the probability of z, right? Z has no influences here, right? So we factorize the joint probability distribution. And now notice that we have a probability of x given z in both the numerator and denominator. Oops. Okay. And so we can cancel those out, and then what we get is just the expression that we already derived up here. Okay. So now we are meant to now find we are meant to find probability of y do x for all values of x and y. And so that's what I'm doing here. Okay. And so there's 4 combinations of y and x. All right. And you can go through each of these if you'd like. Okay. So we'll just look at this first one here. So the probability of y equals 1 given x equals 1. Okay. Well, that is this guy right here, which corresponds to that conditional probability. Okay. Times the probability of z naught, because I'm going to marginalize over z, so I need z naught. Okay. And now I need that expression again, but now this time using z1. Why? Because I'm using both values of z to marginalize over it. And then if you go all the way back up to the question and you want to lay on top the r's and the p's and the all of these probabilities that are described in the question, you can do that. And I've done that here, but like I said, I won't recapitulate that in the video. Okay. Now, part B, we are meant to compute probability of y do x for all values x and y using the adjustment formula. I'm not really sure how this is different than the first question. So the answers here are just what we already went through. So I'm a little bit confused as to why. I don't really know what the difference is between the two questions. I think they're the same question. Okay, so okay, on to C. So now we are meant to compute the ACE, or the average causal effect of receiving the treatment. Okay, and then compare it to the risk difference. Okay, now looking at these two expressions, the average causal effect refers to this expression where we have the do operators, right? Because the do operator, by removing the influence of the confounder, allows us to look at the genuine causal effect of x on y. Okay? Conversely, the risk difference is only using these conditional probabilities, which is not marginalizing over z, right? The confounding factor, and therefore the confounder is very much active here in the risk difference. Okay. So especially if people are more or less likely to receive or not receive the treatment given z, then this is going to be different than that. All right. So I've worked these out. Okay. So here we have the ACE. Okay. And you can just see how this gets expanded, right? So so for this expression right here, right, we need to have y1 and x1 over all values of z, so for z naught and for z1. Okay, right, and so that is this expression. And then I need to, and so what is that expression? It is the probability of of the outcome. I think y1 is recovering, or I can't remember, but what of the outcome y1 given they receive the treatment. Okay, minus the probability of that same outcome given that they don't receive the treatment. And the difference between those is going to be the causal effect of the treatment, right? So anyway, so this would be the expression right here for py1 do x naught, right? Again, we're marginalizing over z. And then again, if you want to take this all the way to the symbols r and p and q and so on, I think that this is the correct expression. Okay. Now, for the risk difference here, okay, we can stop basically right here. The important thing to recognize is that this is not the same expression as this. I think that's the key point here. And then similarly, taking it to the R's and P's and Q's, this is not equal to this. Okay, so I think the thing that's trying to be illustrated here is that the ACE and the risk difference, they are different quantities. Sometimes they can be the same, like I said, if Z is already independent of X or vice versa. Okay, anyway. Okay, and now for part D. So this is again, this is basically a recapitulation of part C in question 1.52. And so I've really just copied and pasted the answer here. But we're meant to show a Simpson's reversal. Remember, Simpson's reversal is when by including or excluding a given variable in our analysis reverses the sign of the causal effect, or I should say of the estimate. I shouldn't say causal effect here because it's not applying to causal estimates. So the example that I gave above in 1.52 was just this. Okay, so here I'm conditioning on Z, for instance, versus not conditioning on Z, and hypothetically one of the answers could be above 0, the other one could be below 0, and this would be an instance of Simpson's reversal. Now, I think that this wants us to give particular values for each of these probabilities, and I'm just not going to do that. It would just be, I think once you understand the concept, that's good enough, and then finding exact values, I'm just not interested in doing that, I guess. So, but I'm also a little bit unclear as to why we are doing that in this question, because notice that these do expressions here, okay, well, by doing x1 or x0, that is conditioning over the effect of Z. And so I believe that these expressions are these expressions, right? So when we're using the do operator, then I don't think that we can have a Simpson's reversal. So let me know if you disagree. I'm not entirely sure about that, but I believe that's true. So anyway, call that good.